So now let's compare this with version 6. Again, remember, why a new version? Well, we don't have IP version 4 addresses anymore. So that's a problem. So out of addresses. That is one motivation. But are there some more reasons? Are there more reasons for, after many years, well, inventing a new protocol? So IP version 6, well, we have this since mid-90s now. And already there we had some more reasons for doing so besides we don't have addresses anymore. There are many more reasons, like address configuration. How do you get an IP address? We will see how this works with version 4 and version 6. How do we at least try to keep the routing tables in routers smaller so that they do not explode due to unstructured addresses? We have some problems here for routing. We had security issues with multicasting, anycasting, some issues there. Quality of service, there were some idea in mobility. We have some advantages with mobile IP version 6 and IP version 6 both, and multi-homing, things like this. So there were some more reasons, as you will see, and also to make processing the packets in the routers simpler, although we have longer addresses. So how do we eliminate the address bottleneck? Well, we go for 128-bit addresses. That's quite a lot, because then we have, in theory, to the power of 128 addresses. That's a lot, and for marketing it was said that, oh, you can have an IP address for each single grain of sand on this planet, etc. Not really true, so there are some limitations and you cannot use all the addresses. I will come back to this. So we have to simplify hierarchies, and also we need to do something about the prefix, so maybe an idea of characterizing certain areas. We also have to support several addresses per interface, as we'll see. But it was not only longer addresses, but also much faster processing of headers, because the headers now get a certain more fixed format. And all the options are now called extension headers. They also follow a certain fixed format, all optional. In normal cases, you don't have these extensions, but you can use, as we'll see. So we also dropped some parts, as we'll see. No more checksum, because the argument is, well, we have the layer 2, and the layer 2 performs already checksumming across everything. So if something happens on the link, and if something happens on higher layers, we have, if we want, layer 4. Plus, as we'll see, we dropped fragmentation. Okay, can we simply do this? Didn't I just motivate in the former chapter we need fragmentation? Now I say we drop it. I will also come back to this. So the protocol, the architecture got simpler. So it's simpler, well, the structure, simpler processing, and that means faster, more packets per second in the router. Also, simpler administration. So we don't need, as we'll see, special protocols like DHCP. We can use it for certain purposes, as I will show, but we don't need. So we can automatically configure IP addresses, IP version 6 addresses, without any additional tools, servers, protocols. So that's the idea. And also we can easily renumber, well, give new addresses to devices just by changing the prefix without changing then the identifier of the device. I will come back to this as well. And then there are some more innovations, like better security integration, also better support for mobile services, multicast, etc. But also interesting, we now support larger packets, plus we have a way for coexistence, but also a way for the migration from IP version 4 to version 6. So if you have to know something about what are brief summary, the core improvements: many more addresses, simpler header, better option support, and in general advances in security, in quality of service, in efficiency, etc. Yeah, many years have gone since the first invention of IP version 4 till we had IP version 6. Maybe today we would design also IP version 6 in a different way, but okay, that's the way it is. Brief overview of the history. It started in the early 90s. There were some proposals for how we can improve the IP protocol, and then some merges, some ideas. So what could be a simple new protocol, and then what is a roadmap in the 94? How can we then really come to a protocol? Until 95, there was the Internet Protocol version 6, the first specification, and the first addresses have been available at 99. So 24 years now we have address and everything. So everything is advised really migrate to IP version 6, and IP version 6 is available in many places. So World IPv6 launch, it was always said that, yeah, in the next year we will have more IP version 6, but in some countries we are still waiting for massive adoption. At least, according to Google, we have more than 40% of all the search queries are now done version IP with version 6. But it's really, adoption is uneven across countries and also across internet service providers. So there are some countries like France and Germany and India that run the majority of their traffic, for example, to Google over IP version 6. And some other countries like the US, Brazil, Japan, they approach something like 50%. But some other countries like Russia, China, they have less than 10% adoption. And some countries like Spain and etc., they have less than 1% of IP version 6 adoption. This is changing fast, but that's just a snapshot. So there's really, the adoption is very uneven, from the majority to less than 1%. Okay, there's still a long way to go, although the protocol is available since, as you see, 95, 96, and addresses since 99. Standardization of IP version 6 touches many fields. You have some key components. So the key components is the base specification of what is IP version 6, and then the updates of the protocols. I will come back to the single protocols we had for version 4, like ICMP for controlling, error control, for example, group management for multicasting, and also the routing protocols I will explain. They also have to know how to handle IP version 6. So some key components, but it also touches some other layers like PPP, like Ethernet, like token ring, FTDI, and so on and so on. So all adapted to the new features of IP version 6. So many, way more than 100 additional standards for how to use IP version 6 in 3GPP, for example, the mobile networks, how to do this, how to do that. But basically we can say IP version 6 today is implemented in more or less all platforms. So on all end systems, all operating systems, all mobile systems, all networking systems, still not always offered by all the service providers. One of the reasons is, well, sometimes you don't get people who really understand how it works. And sometimes you simply say, better I don't touch a running system, so it works for version 4, I really don't touch it. And that's the reason why we'll still have IP version 4. This is the reason why we have, I will come back to this, NAT, so network address translation, all these things. We don't need them any longer, but it's still there. Okay, I will come back to this, but for now, remember, we have to touch all those tiny protocols. Everything that has to deal with IP version 4 now has to be changed, adopted, etc. to the new protocol. But how does it look like? So, packet format. Again, start with the version number, 4 bits. That's identical to version 4, but now we have 6 and not 4 here as a version. Then we have the so-called traffic class. This is exactly where we have our differentiated service code point and our early congestion notification. So they're here and those bits. Then we have something that's called flow label. That's due to a bit of history. In the 90s, we had two competing, complementary, two paradigms of how to provide quality of service. And one was differentiated services, called diffserv. And this is where you have this differentiated services code point from. And the other one was called integrated services, intserv. And this is why we have initially a flow label. So integrated services basically, in short, tried to give a certain data stream, a so-called flow. Well, it was not allowed to call it a connection, but it was a kind of a connection, a soft connection between a server, a sender and a receiver. And this flow of packets then got a certain label, and then you reserved some resources in the routers so that then the routers had enough time, CPU resources, to handle these packets in a special way, so that again you could guarantee end-to-end certain quality of service. The problem was the internet world doesn't like the ideas of connections and keeping states in routers, because this increases complexity. So this is why this was not called connection but a flow, but in the end it was a kind of a soft connection, but it showed that although it was soft, that so you automatically free resources, you don't have to explicitly tear down connections, all this stuff, still too complicated. So it never took off. So we have a part of legacy in IPv6. Today, maybe we wouldn't do it this way. What else? Payload length. So that's important. How long is the packet after the now 40-byte header? The header is double the size. Now we have long addresses. We have something, now that's new. That's the next header. Next header is basically like, okay, like this protocol, what follows on in the next layer. But this time, this could also point to an option. And the options are called extension headers. And if we have a layer 4 protocols, it points to the transport header. We have a hop limit. That was our TTL field. So that's basically the same. Then we have source and destination address. So that's longer, way longer. And then the next header or the payload follows. So if you look at this header and the packet, then you see, okay, we have fewer fields. It is longer, but we have fewer fields. And if we directly compare version 4 on the left-hand side and version 6 on the right-hand side, we see, we do not have, for example, fragmentation. It's not there. This whole thing here, fragmentation. Nope, we don't have this. We also don't have the checksum. It's not there because layer 2 and layer 4, they do the job. We don't do any fragmentation. I will come back to this. We have source address, 4 times the size. We have destination address, so that's basically the same. We have the protocol field pointing to whatever there is as data. Now we have the next header field, and the next header field now points to an option, which is then called next header or the data. So it could be an option, an extension, or it's the data. What else? We don't have header length. We don't need this anymore because, well, it's self-explaining. So basically, we have this 2 times 32 bit for all the first fields, and then we have the addresses, and then we will see what comes as the next header. So that's what the next header tells. We have total length, payload length, so this is pretty similar, and TTL and hop limit, that's the same. So you see, we only keep the necessary fields. And yes, IPv6, the header is longer, but this is mainly due to the addresses and not due to many additional fields. So that's the idea. So having few fields, simpler to pass. It's longer, yes, but simpler to pass. So it's a longer header, only caused by the longer addresses. Better sorted, faster to process. And this is the important part, because the routers, they have to process many packets per second. That's the important thing. And it's not about, reading all these individual fields and doing some processing, some conditional processing, etc. So if we compare, we can say the headers are simpler. So fragmentation, checksum, header length removed. Why? As we'll see, leave the problems to the end host. That's especially true for the checksum, and we want to simplify everything. For fragmentation, we'll see how this works, because it could be the case that there's a link that has a smaller MTU than the starting link on your site, on the sender side. We saw we have a new option mechanism, but this one is simpler to handle, as I will show you. We have longer addresses. We have a flow label. Flow label, yes, with the flow label you could do things, but as I told you, integrated services, that was the original idea, didn't really work out. Never took off. So, okay, so most of the fields are basically explained by looking at IP version 4. The options are different. The options are now called extensions, extension headers. So you can have options, extensions. The idea there is there's a certain specified format of all the extensions, in a way that if I read the field next header, this header tells me what type of extension will follow. So basically it tells me, okay, now this is this and that type. Then I know as a router how to handle it. But the very first thing the extension does is telling how the next header looks like. This could be data, so layer 4, or it could be yet another extension. So basically what we do is we chain extensions if required. And all the extensions, they always have this next header field. Then they tell how long the header is, and then we have the header content. That's the idea. So it's always the same structure. And for IP version 4, we had many different structures, and the routers had to parse all this. So that's the idea. So if I have to include yet another extension, then the next header does not point to data. Then the next header points to another extension. And then maybe this one then points to data of layer 4. And if not, it points to yet another extension. But it's important that each type of extension should appear only maximum once. So if you have a certain extension, then you have it only one time, and you don't have the same extension 3, 4, 5, whatever time. So what type of extensions do we have? So you also see some bit of the history looking at extensions. There are some extensions that are deprecated now. So that was the idea of why not specifying a route. That was the source routing idea, where you tell, this is the path I want to go. Deprecated. There's fragmentation as an extension. Okay, but there's a difference. I told you IP version 6 doesn't do fragmentation, but here is fragmentation. Now, what is the difference? Only the source can do fragmentation, no longer the routers. Okay, I will tell you later how this is done. So, there is no router that does the fragmentation. Well, it's not too difficult. Takes a bit of time. So the sources try to send a packet. If the packet is too large, the source will get an error message and then tries to send a smaller packet. If you still get back an error message, then you try an even smaller packet until you don't get an error message, and this is how you find out the smallest MTU along the path. That's the idea. Okay, authentication, encapsulation, some more options, and there's one option, hop by hop option, and this is what you actually process by the routers. But all the other options are not processed by routers. So fragmentation, authentication, tunneling, all this stuff, that's handled by the sender and the receiver, and the protocol tries to offload as much as possible from the routers, because routers have to forward packets in a very fast way, and they should not deal too much with options, because typically options and error control and all these things, they are handled in software, much slower compared to hardware. So the packet forwarding itself is performed in hardware, not in software. So some examples how this looks like. So a very simple case, the header field simply says the next header is TCP, and then TCP follows. So this is for case for most of the IP packets, IPv6 packets. The next header simply says, well, TCP or UDP or whatever follows. But it could be the case that you say the next header is this and that. Well, not this any longer, deprecated. But that's the basic idea. Or for fragmentation, you said, okay, the next header is this routing, and then the next is fragment header, and then the next header is TCP. So you see how this chaining works. So you pick your extensions and you chain them. So you can have your hop-to-hop extension or some authentication extension or whatever there is, and you chain them if you have to do so. The standard case should be no extensions at all. So that's the fastest case. Again, the remark, each extension should occur at most once. So you do not have several times the same type of a header. So headers are quite, those extensions, are quite flexible. So you can have options there, and well, the option headers, the old ones, in IP version 4, they were a bit different. But now for these IPv6, they're way more flexible, and everything you do is of this type length value type. Remember type length value? We had this long time ago at ASN1. So you have a certain type of option, and then how many bits you have for data. So what's the length, and then the option itself. And important for this, you process all this at the destination. And all the extensions only at destination, but not the hop by hop, because hop by hop, that's something the routers have to do if they support this. Okay, that's the basic idea, so that you have your different types of extensions now. So how does it look like? So you have your next header, and you have your header length, and you have certain options, type, length, data, type, length, data, type, and so on, type, length, data. And depending on the type of the option, this determines the action that has to be taken. So also what happens if I don't know what to do? So then you could say, okay, well, if I don't know what to do with the option, simply discard the packet and don't do anything, or discard and send an error message back to the source, etc. So there are different options what to do if I don't know what to do with this option. Could be the case that I cannot handle it, then this defines what happens. So Additionally, there's a flag that indicates if you can modify data en route. That means if you travel along the path, if routers are allowed to change anything or not. So you see, this is a very flexible scheme, but still, well, a bit similar to IP version 4. It's better not to use any extensions, then you have the fastest way, simple packets. But you have a flexible scheme with the extension headers. There are also today more and more reasons why we at least do this fragmentation. You see, packet size requirements, IP version 6. The standards say, oh, we have at least to have this MTU. Okay, that maybe you start with, you've seen the jumbo grams, so huge packets. Maybe you start with much bigger packets, and maybe it works with, I start with whatever, 10 kilobytes. Then in the normal case, well, we have to do testing if this works. We send it, and then maybe we get back an ICMP, an error message telling me doesn't work. Then maybe I try 5 kilobyte. Okay. Then if I still get back an error, then I know at least it should work, in the worst case, with 1280 bytes. Okay, I tried with larger packets, doesn't work. Okay, that's the normal case, that's in IP version 6. But what happens if we have link that cannot even convey those 1280 bytes? Then we have to perform additional link-specific fragmentation. And this is below IP version 6. IP version 6 cannot handle this. So there are special protocols like, for example, 6LoWPAN that do exactly this. So below IP version 6, additional fragmentation. So because in the world of IP version 6, everything has to convey at least the 1280 bytes. So typically the MTUs are 1500 bytes or more, and this then fits exactly to the typical maximum size of Ethernet packet, so that in the, I would say, most cases, you don't have to do anything. You use your normal maximum Ethernet packet and you can directly send it over IP version 6 around the globe. That's the idea. But this gives you an example for now wireless transmission, where you see, okay, we need something that's below IP version 6, 6LoWPAN, and then we can adapt to the layer 2 protocol, 802.15.4. Mobile communication covers this. Okay, so again, a bit more, this what's called then path discovery. I explained this now already 2 times in short. Now a bit more about this. So we have to find this minimum link MTU of all the links in a path. So you could have your sender going to a router along the path to a router and then to the destination, the receiver. And then you have always a certain MTU, max MTU on all the links. We've seen it's a special case when we go for this wireless things, then IP version 6 cannot handle it. But maybe we have in between, for whatever reasons, we have this 1280 and all the others, they can do the recommended 1500. 1280 is the minimum. Then we have to find out this. So, because the point is, the originating node, our S, assumes the path MTU is the MTU of the first hop. So it assumes, in our case, 1500. And this is why, in this case, we try to send the 1500. And if then a link is unable to handle it, that's exactly this link here, 1280, then, well, this router would return an error message, ICMP version 6 error message, packet too big. Say, I cannot send this out over this link. Max is 1280 for whatever reasons. And this means the originating node, not the routers. The originating node, as in our case, now try smaller packet sizes. So maybe try it with 1280 until it gets no more complaints. And this is then the largest MTU. So why not trying 1400 first and then 1300 and then 1280? Yes, so could be the case. So maybe you have to try several times, but this is the way how it works. Okay, now we saw the IPv6 headers. Please remember, what are the key innovations compared to IPv4? Yes, the length of the addresses, but there are some other innovations that are quite important. We had a closer look into extension headers. So what is the difference now to options, to the option fields? And you can also look this up in literature, how option fields look like, what you can do there, and what we have now with the extension headers, what was the idea. And then we had several times look into fragmentation. So IPv4 offers fragmentation, and IPv6 doesn't offer it anymore. So, but that was required. 6 dropped it. So what do we do now? We don't do fragmentation as such in the network any longer, but what do we do instead?